So, welcome everybody to my talk about predictable vision for autonomous systems. My name is Michael Balszun. I'm working at the Technical University of Munich in Germany, and I should probably set expectations correctly for this talk. When I'm talking about predictability, I mean predictability in terms of temporal behavior. So, predictable response times, for example, of a car. While I'm familiar with the concepts, I'm not an expert in designing neural networks, for example, that can distinguish between a grown-up person and a child, or can distinguish between the reflection of the sun and the actual free horizon. Now, with that disclaimer out of the way, so I think it is clear to everyone that cameras are an absolute crucial part of any autonomous system that is supposed to operate in a non-trivial or complex environment in general. And I mean, there are various reasons why we use cameras. So one is, for example, for relatively low-level control tasks where other kinds of sensors just don't give us the necessary information. So for example, if we're talking about lane following, there's just no other sensor that will tell us where our lane markings are and where we have to stay. And then on the other hand, of course, we need cameras to actually get a semantic understanding of all our surroundings, to understand what's the content of a traffic sign, what's the current speed limit, is a traffic light red or green, what kind of obstacle is in front of me. All this information is essentially just available to us via visual sensors, via computer vision techniques. Unfortunately, while computer vision is a very important and very useful tool for autonomous systems, it also poses quite a few challenges for the system design and for the timing analysis. So first of all, keep in mind, we need orders of magnitude more resources to process a video stream than we would need to process, let's say, the output of an inertial measurement unit or a speed sensor or similar kind of things. So for example, just to analyze a single video frame, you probably need billions of operations. To transmit a fully uncompressed full HD video stream, you need about 3 gigabits per second of bandwidth, and the different buffers that you might have between different stages that work on different chunk sizes also range somewhere from a few kilobytes to actually a few megabytes, and maybe several megabytes if you have to store multiple images even. So the only way to achieve or to satisfy those requirements is actually through a more complex system. Namely, we need additional hardware accelerators in terms of GPUs, FPGAs, or even tensor processing units. And on the transmission side of things, we need to employ compression, at least if you want to transmit the video data over some internal bus system like automotive Ethernet, for example. There's just no way you can transmit an uncompressed image. Now, especially compression now unfortunately also introduces a dependency on the bandwidth requirements. They now depend on the complexity of the scene. Or if you run your compression algorithm in a mode where it has a fixed upper limit, as you would probably usually do in a real-time setting, you now introduce variations in the quality of the image. And especially if your algorithm isn't a two-pass algorithm, where it first checks the data and then decides, okay, how many bits do I spend on which part of the scene, the quality might actually vary pretty drastically. And then also on the processing side, a lot of the processing that is done might actually be per object. So while we still have only one image with a fixed number of pixels, of course, the number of times you have to, for example, run your classification algorithm and over how many pixels you have to run it, this might again change with the content of the scene. Also maybe with the input from other sensors, like the LiDAR first tells you, okay, where there's an object in front of me, and then our other process tells us, now analyze the image in that region and tell me what exactly it is, what kind of car it is, for example. And when you consider all of these effects together, that leaves you actually in a pretty uncomfortable spot, where on the one hand, you don't have a good grasp over what exactly is your worst case scenario and how many resources you will need in the worst case. On the other hand, provisioning excessive amounts of spare resources for that case becomes extremely expensive. So if you just say, well, okay, I'm only using 70% of my system under normal conditions, so to be prepared for worst cases scenarios, then the 30% that are not used are probably the equivalent of the whole processing your car does for all other tasks at the same time. So this is much more expensive than when you would just say, well, I give this Kalman filter a little bit more time if I have miscalculated the worst case execution time of it. So with the ever increasing system complexity on the one hand and effects like data dependent latency on the other, we believe that timing analysis approaches that are purely based on analytical models don't work anymore. So those models either are detailed enough to capture all the details if they are known at all, but then become too complex to be usable in the larger system analysis context, or they abstract away lots of low-level details, but in turn then become overly conservative and lead to huge overestimations of overall response times or necessary resource allocations. Furthermore, as soon as latencies and response times become dependent on the actual input data, it becomes increasingly unclear what actually would be a relevant worst case input. So of course you could compute the worst case input in terms of pixel data that would produce the lowest compression resolution or the longest runtime for a given classification algorithm. However, if that input would be image just displaying noise, then we probably wouldn't care that we cannot compress it or we cannot transmit it fully, or that we have to cut off the algorithm after some runtime. So we believe a much more realistic approach is the use of statistical models of our individual system components that are trained with lots and lots of real-world data that also show, okay, what kind of inputs is what we can expect for our system and what kind of inputs do we have to handle. Unfortunately, we don't have a self-driving car on which we could experiment or generally validate any analysis techniques we come up with. However, what we do have is a very challenging visual serving setup that is built around a sync board. So in case you don't know them, sync boards are a combination of an FPGA part and a classic ARM-based microcontroller. And we use this board to control a magnetically levitated sphere that is captured by a camera system, and then this camera data is processed on our heterogeneous sync board. There we try to figure out where's exactly the tip of the sphere. This information is then fed into a control algorithm, and that in turn again controls the electromagnet keeping the sphere afloat. Now, what makes this setup particularly useful for us is that we have built a quite extensive tracing infrastructure that allows us to trace various events in software and hardware simultaneously at very, very low overhead and without any additional external hardware that might be expensive. More about that later. Let's first have a look at how exactly this system actually works. When we take a closer look at what's happening in our experimental setup, we first of all see a classic control loop here. So we have a camera that at about 180 frames per second takes a picture of the sphere. This image data is then transmitted via Ethernet to our heterogeneous processing system, where the first few stages of our image processing algorithms are performed in hardware, so in the FPGA part. And then the preprocessed image is handed over to the regular processing system, where we just have a Linux running, to finally extract the position data or the position of the sphere, handing over that information to our control algorithm, and this computes then the next actuator action, so the current that's supposed to flow through the electromagnet in our case. To make all of this a little bit more interesting from an analysis perspective, we also added a second data path that goes through a non-real-time system. So we have our second camera running at a lower resolution and lower frequency than the main camera, so this wouldn't be actually suitable for directly controlling the sphere. However, we can use this data and the position that we get from that camera stream to cut out a region of interest in the main image pipeline. So while the data that we get from the secondary node might not have the same low latency and not the same resolution as the main data, we can at least use it as an estimate where the position of the sphere will roughly be in our main image. And then we just cut out a couple of pixels above and below that image. As a result, this drastically cuts down on the processing time in the second part of our image processing that's happening on the software system. And just to give you an impression of what the system looks like when it's running, we made a short video clip where here you're seeing the levitating cylinder. Down here you're seeing a representation of the image as seen by the secondary node. So we have a low resolution image with the detected contours in pink, and the green circle marks the top of the sphere. And here on the right side, you see essentially the same image, just this time taken with the main camera with the higher resolution. But as you can see, the contour detection algorithm runs now only in this very small region of interest window. Now let's get back to why we're doing all of this. Keeping the sphere afloat is of course an interesting control problem, but not our main concern at the moment. What we are interested in is that we have a non-trivial visual serving system on which we can run various tests, try out various algorithms, and then gather a lot of detailed tracing data from which we then can generate our statistical models, and those in turn then can serve to develop and validate higher level analysis techniques. So for this purpose, I'm just exemplarily showing here one short section of a trace that our system could generate, just to demonstrate what kind of information we can log in our system. So first of all, the blue line here is actually a power measurement. So here we are measuring the power consumption of our physical Ethernet interface. And you could count here 56 individual spikes, which each correspond to a single Ethernet frame arriving. Then we have a marker that is created every time the FPGA part generates an interrupt in our software system that tells the software part, okay, the pre-processing is done. Now we can start with the actual with the second half of the image processing. Then down here we have our PS start and PS stop labels, so 3 and 4, which correspond to the start and the end of the image processing on our software system. So here we can measure how long this actually takes for a given frame. Then we're also logging when we get estimated position data from the secondary node, and at which time we are actually using this, which is more or less the same as always when we start the frame, because creating the ROI window is so short that you don't see the difference here. Then, as an interesting detail, we can also store some payload in those labels. And what we do here is we store the age of the ROI information. So here it is the age of the ROI information when it arrives at our system, and here when we actually use it. So that's this number. And in general, so this is interesting because the ROI window in general doesn't have a fixed size. The older the ROI information is, the bigger we make the window, because of course in the meantime the sphere could have moved, and as a result the processing delay, so the time between PS start and PS stop, also changes, because now this algorithm has to work on a bigger section of our image. And of course, once you have all those traces, you can analyze them in various ways and correlate events. So just a simple example, here we have a scatter plot that shows us how the processing time on the processing system depends on the ROI age. And here we see two effects. So for one, we have a saturation effect. And the reason for that is just that at some point the ROI window is so big that it encompasses the whole pre-processed image we get from the hardware. And so it cannot grow any bigger anymore. And the other effect we are seeing are those discrete steps in the processing time. And those are actually the result of an error in the algorithm calculating the ROI window size, because there we have been using millisecond resolution instead of microsecond resolution. And well, that mistake then nicely turned up while looking at the trace data. And with that, we have already reached the end of my talk. So to summarize, computer vision is an absolute crucial element of any autonomous system. However, it also introduces a lot of additional system complexity, and to deal with that in the context of hard real-time systems, we need to start to move from purely analytical models to statistical models that are based on real-time, real-world test data. Now, what I've presented in this talk is our testbed for analyzing visual serving applications. while the actual application we have might not be directly connected to self-driving cars. We believe that a lot of the platform characteristics and also the application characteristics are similar to what we see in a self-driving car or other autonomous systems. So we have a hard real-time application, we have a heterogeneous compute platform, we have multiple nodes that are communicating over a network. And what our platform provides us is an integrated low overhead tracing infrastructure that gives us very detailed insights into the whole processing pipeline on all levels. So including from the lower hardware levels into the software and algorithmic levels. Now, the next step will be to determine suitable ways to transfer this measurement data into simulations and analysis frameworks, and to see how we can use those insights to help in the system design process and in the efficient allocation of resources. And with that, thanks everyone for listening, and I'm interested to hear your questions.